Unit 1, second chapter is mechanical modification. Mechanical modification can be done either by shallow compaction or deep compaction techniques. The advantages of compaction are to increase the shear strength, to reduce the compressibility or settlement, to reduce permeability, to reduce liquefaction potential, to control swelling and shrinkage, and to increase the durability. So it also decreases the differential settlement. Principles of densification. Densification under static or leading pressure. It is effective for densifying unsaturated cohesive geomaterial. Then densification under dynamic loading using vibration or impact. Vibration or impact is effective for densifying unsaturated cohesionless or collapsible geomaterial. The next principle is densification due to liquefaction. Vibration or impact can also be used to densify saturated cohesionless geomaterial by inducing liquefaction to the geomaterial. The next principle is densification due to consolidation. As we know, saturated cohesive soil is difficult to be densified using normal compaction techniques. It has to be densified by removing the pore water from the soil, which is called consolidation. Compaction. If we observe the compaction process in the field, it will be done by using various compaction equipment, and it will be done layer by layer. The thickness of each layer is limited to 300 millimeter. The water will be sprinkled on the soil before compaction. To estimate the maximum dry density and optimum moisture content, we will conduct the compaction test in the laboratory. So what are the applications? The applications are for compacting the subgrade soil of pavements, embankments, dams, slopes, parking lots, etc. So the main limitations of this method are the depth of the improvement is limited. For compacting the thick deposits of loosely filled soils, it is not an effective method. So it is mainly used for compacting the new layers of soil above the existing ground and not effective for in situ natural deposits of soil. As the maximum density will be obtained at optimum moisture content, it is difficult to bring uniform moisture content throughout the soil and also difficult to achieve same degree of compaction effort at different depths of soil deposit or layer. Laboratory compaction test. To conduct the compaction test, the volume and weight of the mound are determined. The field soil is woven dried and mixed with the known percentage of water. This wet soil is placed in the mound in 3 layers, and each layer is compacted by giving 25 blows per layer with standard rammer. The weight of soil is determined and bulk density is estimated by taking the ratio of mass of soil to volume of soil. The water content is estimated using woven drying method and the dry density is determined. The water content is increased and the process is repeated to get set of water content and dry density values. A graph is plotted between water content and dry density, which is called a compaction curve. The peak of this curve represents the maximum dry density and its corresponding water content is reported as optimum moisture content. If the soil is compacted with a water content less than OMC, it is called dry of optimum, and if the soil is compacted with a water content more than OMC, it is called wet of optimum. So in case of expressways, modified compaction test has to be conducted, where the soil is compacted in 5 layers and the weight and height of fall of the rammer are also more. The maximum dry density obtained by modified test is more than that of standard test, but the OMC is less than that of standard test. The theoretical dry density can be determined when we take percentage air voids as 0 in the dry density equation. When we plot these values, we can get the zero air voids line, which is also called as saturation line. Then what are the factors affecting compaction of soil? Water content. As the water content increases, the dry density increases up to OMC and then decreases. Then amount of compaction. As the compactive effort increases, the dry density increases. Types of soil. The dry density achieved by coarse grained soil is greater than that of fine grained soil. Then methods of soil compaction. The maximum dry density also depends on the type of compaction equipment, type of machinery, and also time of compaction. Addition of admixtures. Addition of admixtures like lime, fly ash, GGBS, bitumen, etc. also alters the compaction characteristics of the soil. Effect of compaction on properties of soil. First one is effect of compaction on soil structure. Soils compacted at a water content less than the optimum generally have a flocculated structure. Soils compacted at water content more than the optimum usually have a dispersed structure. Then second one is effect of compaction of soil and permeability. The permeability of soil decreases with the compaction due to increased density and better orientation of particles. So this permeability of a soil also depends on the size of voids. The permeability of a soil on the dry side of optimum water content is more than that of wet of optimum. Then third one is swelling. Soil compacted dry of optimum has high water deficiency and subjected to more swelling. Fourth one is pore water pressure. The pore water pressure is less for soil compacted dry of optimum than that of wet of optimum. Shrinkage. The soil compacted dry of optimum shrinks less when compared to wet of optimum. Compressibility. The soil compacted dry of optimum is more compressible. Stress-strain relationship. The soil compacted dry of optimum will have more modulus of elasticity. Shear strength. The soil compacted dry of optimum will have more shear strength. Then field compaction methods. There are various types of compaction equipment in use depending on the soil, site conditions, and economic considerations. Suitable equipment is selected. The commonly used compaction equipment are dampers, rollers, and vibratory compactors. The compaction achieved in the field depends on contact pressure of the equipment on the soil, which depends on contact area of the machine with soil, number of passes of the equipment on the soil layer, thickness of layer, and also on the speed of the roller. The field compaction equipment are basically divided into two types: light soil compacting equipments and heavy soil compacting equipments. Light soil compacting equipments are used for compacting smaller areas by using rammers, vibrodampers, vibrating fluid compactors, etc. The rammers produce impact load and are suitable for compacting corrosive soils. The base width will be around 15 to 20 centimeter. They are suitable for compacting corrosive soils in trenches and very small areas, and have the ability to compact deeper amount of soil than a plate compactor. Vibrating plate compactors are used for compacting coarse grained soils with 4 to 8% fines only. Compactor plates are wider than rammer plates, and they use vibrations to help settle the soil as it compacts. The weight of this equipment vary from 100 kg to 2 ton, with contact area varying from 0.16 to 1.6 meter square. The vibro dampers are suitable for all types of soil and to compact smaller areas. They are light in weight compared to vibrating plate compactors and are easy to operate. The weight of this equipment vary from 50 to 100 kg. Then heavy soil compaction equipments. If the area is large, then heavy compaction equipment is preferred. There are different types of rollers. First one is smooth wheeled rollers. Smooth wheeled rollers are of two types: static smooth wheeled rollers and vibrating smooth wheeled rollers. Static smooth wheeled rollers have one large drum in front and two steel drums on the rear side. These are generally used for compacting gravels, sand and crushed rock. The gross weight of these rollers is in the range of 6 to 10 tons. The weight can be increased by filling the drums with water or sand. The desirable speed and number of passes for appropriate compaction of soil depends on the type of soil and varies from location to location. About 8 passes are adequate for compacting 20 centimeter layer. Then a speed of 3 to 6 km per hour is considered appropriate for smooth wheel rollers. Vibrating smooth wheeled rollers. In this, the drums are made to vibrate, which increases the efficiency of the roller. Even the depth of compaction is more compared to the conventional smooth wheeled roller. The weight of drums can be increased, as in the case of smooth wheeled rollers, by ballasting with water, wet sand, or by mounting steel sections. Next one is sheep's foot roller. For compacting heavy clays and silty clays, sheep's foot rollers are effective. These rollers are employed in road and rail projects. They have projecting legs on the drums which provide leading action. Sheep's foot rollers are of static and vibratory types. Vibratory type rollers are used for compaction of all fine grained soils and also soil with sand gravel mixes. Generally, this roller is used for compaction of subgrade layers and also for sand gravel mixes. Generally, this roller is mainly for rail projects and subgrade layers in road projects. The efficiency of this roller depends on the gross weight of the roller, contact area of the projections and their spacing also. The pressure is maximum when a foot is vertical. Then the third one is pneumatic tired rollers. This kind of rollers are used in earthwork and bituminous works. The front axle may have 4 smooth wheels, whereas there can be 5 wheels on the rear axle. These wheels in a row give uniform pressure throughout the width with the leading action. Generally, 8 passes are sufficient to achieve the maximum density. The total weight of the roller can be increased from 11 ton to 25 ton or more by ballasting with steel sections or other means. Next type is grid rollers. These rollers are useful to compact the stones and rocks and are not suitable for clay soils. They are made up of cylinders with steel grid. They provide high contact pressure but little kneading action. Typical weights vary from 5.5 tons to 15 tons when it is ballasted. Then other type is tamping rollers. These rollers are similar to sheep's foot rollers with the lugs of larger area than sheep's foot rollers. Their efficiency is very high compared to sheep's foot rollers and best suitable for compacting coarse soils. Deep compaction techniques. When the loose soils are deep, roller compaction is not effective, and deep compaction techniques like vibrostabilization, dynamic compaction or blasting are required to compact the soil. There are three types of vibrostabilization technique: vibro compaction, vibro displacement and vibro replacement. The vibro compaction method is used for stabilization or compaction of deep layers of non-corrosive soils. The vibrating unit which is called as vibrofloat is of length around 2.1 meter is attached to a pipe which is lowered into the ground gradually up to the desired depth. Due to this vibrating effect, the void ratio of the soil decreases and density increases. This process can be used in both the dry and wet conditions of soil. The next step is vibro displacement method. This method is used for compacting coarse soils. The process involves the penetration of the vibrator into partially saturated soils, resulting in shear failure of the soil, which then gets displaced, forming a cylindrically compacted zone. Next technique is vibro replacement technique. This method is also used for coarse soil, but here the vibro float is having openings at top and bottom for water jets. Initially the vibro float is lowered into the ground with a jet of water. Then the water is pumped out from the pit. The vibro float is lifted slowly with vibrating effect, which compresses the surrounding soil in the pit. The vibro float is raised in lifts and gravel or sand is added from the surface to compensate for the loss of volume caused by the increasing density. The vibro float is introduced into the soil in a triangular or square grid with a spacing of 1.5 to 5 meter and depths of 3 to 20 meter. Next deep compaction technique is dynamic compaction. In this method, a heavy weight of about 15 to 40 ton is dropped from greater heights like around 10 to 30 meter to compact the granular soils. The heavy weights are lifted with crane and allowed to fall on the marked locations on the ground. The vibrations caused by this action increases the angle of internal friction and density. This method is useful for machine foundations with impact loads. This method is effective up to a depth of 10 meter. The drop locations will be triangular or square grid pattern, the spacing of which is determined by the subsurface conditions. Then compaction control procedures. How to control the compaction process in the field. After the compaction process in the field is completed, the dry density has to be determined to verify whether it has achieved the required density or not. So how to find the bulk density? To find the bulk density, we can use either core cutter method or sand replacement method. But for the measurement of water content, since the oven drying method takes 24 hours, we will be using Proctor needle method to estimate the water content indirectly. So here, after finding the water content using the Proctor needle method, we can estimate the dry unit weight in the field. So then we have to calculate a parameter called relative compaction, which is equal to maximum dry density obtained in the field divided by maximum dry density obtained in the laboratory. This value should be greater than 95. If it is below 95, then the compaction process at the site has to be repeated.